Okay. So thank you. Thank you, Marcos. Thank you.
So to start the second day of talks, today we will have Daniele Faenzi from the University of Bourgogne, Dijon, and he'll talk about Ulrich bundles on cubic fourfolds. Daniele, please.
Yes, thank you. So I I would like to thank you, Marcos, and thank you all. Thank you for this nice organization. So I feel very responsible now because everything is recorded, so I should be very careful about what I say. So unfortunately, I couldn't arrange things so that my talk starts with the song by Gypsy King. I couldn't make it on the PDF, but yeah. Anyway, so let me start by some introduction on Ulrich bundles. So I'm lucky because somebody already introduced this topic. So, so I can make it shorter on introduction. Okay, so I hope you see what I write. So we already saw Ulrich definition of Ulrich bundles and motivation to study it. Thanks to the talk by Vincenzo. So let me just specify what happens for more concrete case, namely for hypersurfaces. So general definition of Ulrich, see Vincenzo. So the case we are interested in today is for hypersurfaces. So I take X, a hypersurface. So a hypersurface of degree D, say at least 2, so defined by a form which, so let me take the opportunity to fix some notation in the polynomial ring in n plus 2 variables, and K here is an algebraically closed field. Okay, and so Ulrich sheaf on X is a coherent sheaf with so you can take this as a definition, just a shortcut for the Ulrich condition is this. So the cohomology must be entirely 0 in some twists. So T should belong to 1 up to n. So the cohomology should be entirely 0 for n consecutive negative twists. So by the way, this implies that the reduced Hilbert polynomial has n consecutive roots, and it turns out that it equals, so for me this is a notation for the reduced Hilbert polynomial, namely the full Hilbert polynomial divided by the rank. This is finally, this must take this form, d over n factorial and then product of t plus I for I that goes from 1 to n. Here are the n consecutive roots. So as Vincenzo mentioned, one of the main points about Ulrich bundles is their existence. So for hypersurfaces, actually, this is not really an issue because there is a theorem by Backelin and Herzog says that E exists. So Ulrich bundles always exist on hypersurfaces. So actually, the question we are interested in today is about the rank. What is called Ulrich complexity, UC of X. So the minimum. So R here is the rank of an Ulrich bundle, Ulrich sheaf on X. So this is what we are actually interested in today. And this is a widely open question. So essentially we know pretty much nothing about it, but some cases we know. So something we know. So my introduction is basically an overview of what is known about Ulrich bundles on Ulrich sheaves on hypersurfaces. So say X is smooth and D equals 2. So X is just a quadric. Then in this case, the Ulrich complexity is 2 to some exponential of 2. And actually, E is a spinor bundle. So any Ulrich bundle is a direct sum of spinor bundles, and this minimum rank is this. So you see the rank could be quite high anyway. So yeah, by the way, I told you about Backelin and Herzog, and Backelin and Herzog gives you very high. So Backelin Herzog gives a very high lower bound, upper bound. Sorry, upper bound for UC. So the thing provided by Backelin and Herzog is in general a very, very high rank. And for quadrics, we know that the rank is actually very high, but anyway, lower than Backelin and Herzog's rank. And so another case we know is for n equal 1. So for curves. So actually, you see X then is 1. And E is a line bundle of degree G minus 1 lying outside Riemann's theta divisor. Theta divisor in the Picard group. Actually, here this lives in X hat. So X hat is the normalization. and E is actually the pull down of a, so maybe just say that X is smooth, and then we have Ulrich bundles are just generic line bundles with respect to, yeah. So this is one case we know. And for higher rank or so for higher, sorry, dimension or D, we know much less. So for n bigger than or D at least 3, in general we know UC is pretty much unknown in general. And however, for dimension 2, we have some cases which could be interesting also for the rest of the talk, so let me mention them. So for degree 3, so for cubic surface, so UC is 1 unless X has a 6 singularity, a E6 singularity. This is a Bandoleros. So this, I mentioned this just to mention that for singular, so the minimal rank of Ulrich sheaf could depend on singularities of X. So for some singular cases, this could be higher than generically, okay? But anyway, so let us assume from now on that X is smooth. From now on, I mean, for the rest of the talk, I will assume that X is smooth. So maybe just to be a little bit more precise, again, for cubic surface, X is then blow up of P2, you know, at 6 points. And so in this case, E is a line bundle of the form OX of C, where C is a twisted cubic. And there are 72 of them. 72 non-isomorphic Ulrich bundles on a smooth cubic surface. So they are like, so I will not write all of them, but so C could be the pullback of a line. You know, if I map down to P2, blowing down, or it could be something like 2C minus E1 minus E2 minus E3, or maybe C3 minus 2E1 minus E2 minus whatever minus E5. So, you know, you need to have degree 3 curves and that are rational. So for instance, I need to impose a double point in case it's a cubic, a plane cubic, to make it rational, and then degree 3 and so on, etc. And the last one is 5L minus 2E1 minus, with all 2's. So this is a curve, a plane quintic, which has genus 6, and then 6 double points, so it has genus 0 and degree 3, and that's the last case. So this is to mention the kind of things that one could find when one looks for Ulrich bundles. For this particular case. And then there are more examples that we know. For example, d equal 4. So in this case, UC of x is 2 unless x lies in some Noether-Lefschetz divisor. In which case we have Ulrich complexity 1. So this is another thing that I wanted to mention. So before I told you that for special cases, so when x acquires some singularities, the Ulrich complexity can go up. Well, for special varieties, the Ulrich complexity can also go down. So in this case, generic quartic is a K3 surface and it has a Ulrich bundle of rank 2, but special ones could have Ulrich bundle of rank 1. Okay, so this is not quite clear how Ulrich complexity notion specializes, so it can go up or down. And well, so okay. So this was proved originally by Emre Koskun. Which I am probably mispronouncing. So they proved it for all K3 surfaces, for all quartic surfaces. And then, you know, one can also ask the question for any K3 surface and so on, but this is not the point now. So for n equal 2, again, and d maybe between 5 and 15. So UC is 2 for x very general. This was proved by Beauville, Schreier. So Schreier constructed Ulrich bundles of rank 2 using Macaulay 2. And Beauville proved that so the Ulrich complexity is at least 3 for higher degree. Okay, so I think for surfaces we don't know about what should the Ulrich complexity be for high degree. So, and just to finish this overview, let me spend a word on threefolds. So for d equals 3, the Ulrich complexity, so here let's say x is smooth. So okay, I said I would assume x smooth for the rest of the talk, so it's okay. So this is 2. So this is related to Pfaffian representations. Also for d equals 4. I think this is 2, except maybe some x with non-reduced Hilbert scheme of lines. So the Hilbert polynomial of a line is t plus 1. Hilbert scheme of lines can be sometimes non-reduced. And for those, I'm not sure about the Ulrich complexity. So for d equals 5, Ulrich complexity is 2. Say for x general, there are finitely many. And we don't know how many. So this is a finite number, but we have no clue about this number. And for d bigger than 5 strictly, then the Ulrich complexity is at least 4 as far as I understand. This is from Ravindra and Tripathi. And again, I think nobody knows about which number greater than 4 we should expect. Well, I don't know if nobody knows, but I don't know. Okay, so this is the situation. So you see that there are very little things, very few things that we know. And essentially we know them for very special cases and for typically for generic hypersurface of a given degree. If the dimension is low and degree is low, we can say something. Otherwise, it's difficult. So, do you have questions?
I have one.
Are you still there?
About the complexity of the case D greater than 6, right? So how do you usually get these results about the Ulrich complexity needed to be greater than 4? Like, do the case equal to 3 gives you something about the topology of the X?
Yes. So okay. So one thing is you can compute the classes of so you know that Ulrich bundle has a certain Hilbert polynomial, and then by a Riemann-Roch you have restriction on the classes, on the Chern character, say, of your sheaf. And in case you assume the hypersurface is very general, then you have control on the cycles and on the cohomology of the hypersurface, and therefore on which classes can appear. Okay?
Okay. Yeah.
The intersection, you know the intersection ring, and then, yeah, so typically when the hypersurface is general, most of the cohomology is inherited from the ambient space, except in some middle degree and so on. So you can argue on that and say that many cases are impossible, and that leads you to exclude some ranks.
Okay, thank you.
Yeah, about so for this particular case, rank 2, actually this is related to Pfaffian representations. So it is a bit easier to say that, for instance, for n at least 5, the Ulrich dimension must be at least 3. The Ulrich complexity must be at least 3, because a Pfaffian representation would give you some singular locus then of the hypersurface. So actually playing with the singularities and the cohomology of the hypersurface, you can somehow rule out some cases and obtain some lower bounds.
Okay, yeah.
Okay, but anyway, this result by Ravindra and Tripathi is actually more subtle than this. So they really make some computations with these Pfaffian representations, and they use heavily the genericity of the hypersurface. So here maybe I should add an axis general, or maybe very general. Actually, the proof is quite involved for this case.
Daniele, and I guess the original result by Balkeith and Herzog also give you upper bounds for the complexity.
Which results? I'm sorry?
The original result that you mentioned by some guy with D and Herzog. Because they prove existence. Buckling, yeah.
Yeah, so they
because
provide
they prove
the
existence from very high.
Where is it? It's around here. Yeah. So it gives you an upper bound because the Ulrich complexity is at most what they find. And this thing that they find is very high.
Okay, thank you.
So they really give some existence. This is a sort of combinatorial way to, depending on the equations of the expression of the hypersurface, of the defining a polynomial of the hypersurface. But it's exponential in the number of monomials and so on, so it's very big. Okay, so do you have more questions? Right, so, okay, so now let us start the talk. Sorry, I know that half of my time is over, but anyway, so today's theorem is the following. So let X be a smooth cubic fourfold. So n equals 4 and d equals 3. Then X admits an Ulrich bundle of rank 6. So combining this with some previous result by Kim and Shire, so for X very general, then the Ulrich complexity is 6. So maybe some remarks. So first thing is, okay, so Ulrich complexity is at least 2 when X is smooth, because there can be no line bundle other than just O1 because of, Lefschetz theorem. And so if the Ulrich complexity is 2, then, this is if and only if X is Pfaffian, fourfold, and then X is rational. Well, it could be somehow that this is related to rationality, I don't know. Anyway, if the Ulrich complexity is 2, then it's rational. And so if X is very general, then so the rank is a multiple of 3. This is again Kim and Schreier. And so I don't know what happens if so the Ulrich complexity of X is 2, 3, 4, or 5. I know that there is some work in this direction by Wong and Yin, but I don't know exactly what the result is. So the cubic fourfold could support Ulrich bundles of rank 3, 4, and 5 in some cases, but I don't know what sort of condition that implies on the cubic fourfold. I mean, it implies that the fourfold contains some kind of surfaces, but I don't know if this is again another Lefschetz divisor in the moduli space or something like that. So anyway, probably it's some Noether Lefschetz condition, but I don't know exactly about it. So do you have questions about the statement? Okay. Okay, so the rest of the talk is devoted to survey of things and ideas that we could use to prove this. So I'll say ideas and techniques that we use to construct this rank 6 Ulrich bundle. Okay, so let me start with so the basic ingredient is twisted cubics. So X contains twisted cubics. Twisted cubics, I mean rational normal curves of degree 3, really smooth, just plain definition of twisted cubic. So how you find a twisted cubic? Well, you just cut with a cubic surface, and we know that a cubic surface contains twisted cubic. So this C will be contained in some P3, which is the linear span of C. And so Y is, so I call this V. Y is V cut with X is a cubic surface. This cubic surface could be badly singular, but we will take one that is smooth. And irreducible, of course. And then, so the first ingredient is that we have resolution of this over V. So as Vincenzo told us yesterday, this looks like this. It's a linear resolution of just one step because it's a hypersurface. And then if you restrict to Y, this thing, so this M So this M is just the equation of Y in V. Maybe if I go really back to the beginning, we already saw this. Where is it? Oh, no, we didn't see this because I forgot, but doesn't matter. Anyway, this M is a matrix whose determinant is an equation of this. So when I restrict to Y, then this determinant vanishes, and so here we have a kernel. And actually, this is the whole stuff about matrix factorizations. So here, this one has a, so restricted M, here you have M star, some matrix related to just the co-matrix. So, you know, M and M star are, their product is the determinant of M times the identity, and so it's 0 over Y. And this continues in a periodic way. So this is result originally due to Eisenbud. So this is 2 periodic. And here we have a kernel. Here we have another kernel. So here this one is periodic. So this is just OY of C minus 3H. So that maybe I call just H the O1. And here there's another guy, which we will talk about later. Anyway. And also, one thing we need is that, so you can notice that, oops. So what I call CT, the transpose of C, is defined by 2H minus C, is again a twisted cubic. It's actually defined by the transpose of M. So, you know, in the example we considered before, so CT, if I write it like 2H, so 2H is a 6C minus the sum of 2 times EIs, with EIs the exceptional divisors as before, minus C. So this is the other twisted cubic, one of the twisted cubics I mentioned before. Okay. So so this is just to point out that we have some matrix. Its transpose gives you another somehow residual twisted cubic, and so this is a one construction. And so the main point here is that the Hilbert scheme of twisted cubics so I write M3, it's a component, the irreducible component of the Hilbert scheme with this Hilbert polynomial 3t plus 1 of x containing C. So M3 is a 10-dimensional smooth irreducible manifold projective writing. And so there is a map that goes from M3 to some Z prime. So this map is obtained by considering the linear span of each twisted cubic. So it's a map to the Rosmanian. Maybe this map is only rational. And this Z prime also has another it has a contraction to a Z. So this is a contraction to Z, which is so this Z is a 8-dimensional projective hyperkähler variety. So this is a maximal rationally connected. So the rational connected quotient of the result of applying the rational connected quotient to M3, and this is actually the result by Lane, so Christian Lane, Manfred Lane, Sorger, and Van Straten. So they proved this this stuff about the Hilbert scheme. So the Hilbert scheme has a quotient which is 8-dimensional hyperkähler manifold. Actually, one of the few hyperkähler varieties that we know about. So this is a deformation equivalent to some K3 4. So Hilbert scheme of 4 points on a K3. So we will need this Hilbert scheme to make our construction. And actually we need another way to see this Hilbert scheme, which is due to in this form to a different view on Z prime on this hyperkähler eightfold. So it is this thing. So you take, so you think of O, Y, C. Actually, I need the transpose rather, but anyway. So this is a line bundle again on Y, but you can see it as a sheaf on X, and it has 3 sections. And it's generated by these 3 sections. And then this gives you a sheaf here, which I denote by GC. So GC is so if you are familiar with mutations, you can think of it of the mutation. So left mutation of OYCT through OX, or anyway, it's just a kernel of the natural evaluation map of global sections. So this GC is a Giesecker stable. So you see that all the twisted cubics which lie in the same cubic surface are associated to the same GC, okay? So there is a P2 worth of such twisted cubics, and this is the P2 actually. So this M3 to Z is a P2 bundle, which is just this construction here. And so it is a result by so Laos, and again Lane, the Christian Lane, and Macri and Stellari. So they proved that the moduli space of GC is Z prime. So you can recover the Z prime not as a quotient, but just directly as a moduli space of some sheaves. And these sheaves have the same churn character as GC. Okay, so that's it. So this is some background stuff on twisted cubics that we need for this, and then we need to go to syzygies. So I just write sigma I x of f for, so if I have f, a coherent sheaf, and I start taking a minimal graded free resolution, sheafified, so this is di. So this image here is my i's syzygy. So fi is some O of x of ij. Okay, minimal graded free resolution. So I just call sigma I this ith syzygy. So actually I need to take something that I call SC. So it will be the fourth syzygy over x of OC. Well, actually I put a 5 here just to make the degrees more comfortable. So what do I do? So we start with a twisted cubic. We know many things about the Hilbert scheme of twisted cubics. We know it's related to hyperkähler manifolds. And so one way to think of twisted cubics is to associate to it this GC. And another way is to associate it syzygy, which I call SC. So actually I want to construct vector bundles, so I need to go far enough in the syzygy. So here I wrote for you the resolution of so this thing, the minimal resolution when the sheaf is OC. Just forgetting the 5. So you know, here is a sigma 1 of x OC. Here is sigma 2. Here's sigma 3, and here is sigma 4. So actually, so this one is already locally free, and this is also locally free. So all of them from now on to the left on are all locally free, and we also have a resolution of them. So you can look at the rank. So here it's 1, here it's 4, here it's 6, and here again 6. So again 6, and then here there's something else which is 6, and then 6, and so on. Okay, we have this kind of resolution. Okay. And then, so there's a, so the first lemma says that SC is vector bundle with so H1 of SC. So when I put a star, it means that it vanishes in all degrees. So this was called ACM bundle. And so H star of SC minus T is 0 for T in 1, 2. So actually H0 of SC is not 0, this is 3K. And we have O30 to SC. And here you get this GC. So this sheaf by Laos and others is somehow part of the syzygy construction. Here, this 3, you can see it here. So this 3 is just this 3. Okay, there's 3 sections appear here, and they give you this exact sequence. So I don't know how much time it would be left, but so I'd like to give you some idea of how to, starting from SC, to construct the Ulrich bundle. So
you have more or less 10 minutes.
10 minutes. That's cool. Okay, so part 2 is so in elementary modification. I'll try to be very quick on this. So the idea is start from SC and construct I need to construct an elementary modification. So that means that I take a sheaf which is closely related to SC, but which differs from SC along a codimension 2 subvariety. And this codimension 2 subvariety is again Y, the cubic surface. So I do like this, SC OYD. And here there is this E to construct E as kernel fitting into this, and in such a way that H0 of this, so this I call eta of eta, is iso. So remember, SC had 3 sections, okay, and OYD also has 3 sections, and so I want these global sections to be just the same. So actually, we can do this choosing appropriately D. So D is another twisted cubic with some intersection. So D is again in Y, in the same cubic surface, but I need that C intersects D at 2 points. So for instance, if C is so in the blow up notation, for instance, B could be 2C minus E1 minus E2 minus E3. So I have to do this because actually this goes through this question mark sheaf here. So it goes through observing that okay. So here, let us go back to the question mark. So it was like this, OC T actually 3. I need to take something like this. So R is the R of 1 is actually the pullback from the blowdown map of omega 2 of P2. Blowdown. And then this way I can construct R1 a surjection like that. Actually from the fact that the cotangent bundle of 2 surjects onto O of ideal of 3 of the 6 points twisted by 2, and with a kernel which is just O1, I think, no, O minus 1. And so you see, when I pull back this gives O of 2C minus E1 minus E2 minus E3, which is just OD. And so the global sections here are just isomorphic. So, so using this eta 0, I can reconstruct eta. So this is a lemma using some by some lifting. Via some vanishing of cohomology. Okay. Okay, so the last 2 minutes, maybe, if you allow me, Marcos.
Yeah, go ahead. To conclude, 2 minutes.
Yeah, cool. So the last thing is to deform E to Ulrich bundle. So the thing is, this E we started with is not locally free. It is, but it has some vanishing, which is nice. So so E has let's say the Hilbert polynomial of Ulrich, the reduced Hilbert polynomial is the same of Ulrich, and So it has h star of e of minus t 0 for t in 0, 1, 2. Actually, not quite Ulrich, but rather Ulrich of minus 1. So we only need the extra vanishing minus 3 for some deformation e prime of e. Then it's Ulrich. Then e prime of 1 is Ulrich. And so this is done using this this Kuznetsov category. So the thing is that the derived category of X is of the form Kuznetsov category of X O1, O2. And because of the vanishing, E lies in the Kuznetsov category, which is a K3 category. And so, so by results of Bayer and other people, E deforms nicely. So by this, I mean that there is a smooth scheme of the expected dimension where E deforms, which is the universal deformation space of E, and then so the final technical part is to show that generic element in this deformation space, which is a kind of two copies, so maybe the generic element in this deformation space is Ulrich. So this has to do with a Lane Sorger van Straten eightfold twice. So I cannot be more precise. But so we use the these sheaves G of rank 3 to show that the generic element is not an extension of such. So it goes out of two copies of the Lane Sorger van Straten eightfold, and this is somehow enough to show that it is actually Ulrich. So I'm sorry for going over time. I will stop here.
Thank you, Daniele. Are there any questions?
Daniele, I want to just ask you a question.
Yeah.
So you need the modification, the elementary modification to deform this, or?
Yeah. Okay. So we need the elementary modification to get the right Hilbert polynomial. So I know that we know what the Hilbert polynomial of an Ulrich bundle should be. So I know that this S doesn't have the right Hilbert polynomial. Okay.
Okay. Okay.
So it does up to something. Up to so this Hilbert polynomial, we are on a fourfold, so it's a degree 4 polynomial. So the Hilbert polynomial is good up to degree 2. So I should modify it in degree 2. And so so the difference between the Hilbert polynomial we want and the one we have is the Hilbert polynomial of this guy.
Okay.
So somehow we need to take the difference, and this difference is made by this modification. And then the problem is that this modification gives you something which is not locally free precisely over this locus, over this surface. And so roughly speaking, so the idea is that we have to move out of the space of those sheaves which are not locally free. And roughly speaking, we prove that they can only fail to be locally free along such surface. And then by some dimension count, we check that this locus is too small. And so the generic element is not in that locus, and so it's locally free.
Okay. Why this the final deformations, they do exist?
Sorry?
So why the final deformations in the last page?
Yeah.
Why they do exist so that you can deform this to an Ulrich?
Okay, so
I mean, if you can say something about this buyer and
yeah, this is so this is the one of the main points actually. So you know that for K3 surface, the moduli space of simple sheaves is unobstructed. It's smooth at any point. At any simple sheaf, you have a unobstructed deformation space. So this is what happens here. It is not a K3 surface, but a K3 category. But somehow things behave in the same way. So this is what they prove. Okay, so actually, because of the K3 category, here we have, so X, okay, we compute X1 of E, this is a 26. And X, so E is simple. Maybe let me put this here. So E is simple. So it lies in this K3 category. So X2 of EE is third dual in this Kuznetsov category to X0 to home. So this is one dimensional. So this could provide obstruction, but actually it's not obstructed. And here, this is the thing they prove. So it uses this Buchweitz-Flener deformation theory. Okay, so it relies on the TIA class and so on. But it's a bit involved if I have to go into the details. But anyway, the idea is to reformulate the theorem on K3 surfaces for K3 categories, and then it gives you this unobstructedness.
Oh, thank you. Okay.
Thank you, Amar. So maybe we leave other questions for later.
Yeah.
We are getting into the next talk, and thank Daniele now. Thank you, Daniele.